currently, are they in a, is it in a separate kind of room and then they all join, or is it all just doing?
Yeah, exactly. It's
Ah,
it sort of opens up to participants after we hit webinar start. Hi, everyone. Thanks for attending today. We'll be starting today's presentation in just about a minute as more people arrive. Great. Okay. I'm going to say we can begin to get started now. So thank you all for attending today's lecture. This is our session on earthquake location. And we're really happy to introduce our presenter today, Jonathan Smith. Dr. Smith received his PhD from Cambridge University in 2019 and is currently a postdoctoral scholar at Caltech working on machine learning-based earthquake seismology, sort of as applied to problems such as phase picking and earthquake location. So without further ado, feel free to take it away.
thanks for the invite and thanks for the kind words. So I'll start by sharing the screen. Okay, can you hear me okay? And can you see the screen?
Yep.
Perfect. Okay, so today I'll be discussing earthquake location, and I've put together this Jupyter notebook hosted on a service called Colab, or Google Colab. And this is a service that allows you to run a Python Jupyter notebook on one of their free architectures or their free CPUs or GPUs and process through the notebook in turn. So I'll first discuss the outline of this course, and then I'll go through a bit more information of how this notebook works and how you can get to grips with processing the code along with the talk that I'll give. So let's start by pushing that up and going through it. So the presentation today is kind of separated into 4 main sections. The first one will be installing the packages required for the notebook throughout. The second one will be going through a multi-seismic station grid-based earthquake location. What this will do is it will give us a background to a very simple earthquake location problem, and kind of starts in the early stages of earthquake location theory with ray-based methods. And this is just simple misfit functions. But they will then go on to discuss more complex cases, such as probabilistic earthquake location. And this is including some additional information on uncertainty in the observational data. And finally, we'll bring together in some discussions and conclusions section, kind of what we've learned throughout this notebook. And although it's on a very simple problem, and this will be discussed a lot more in the early section, we'll also go into a brief understanding of how you would include more complexity to the problem. And this may be more realistic subsurface velocity structures, or even improving the computational speed at these earthquake locations, which would become more of a issue with larger number of observations. Okay, so those are the 4 main sections. So we'll start with section 0, as it's more a setup than an actual going into information. So to go through these notebooks, you will have a link on the GitHub supplied by Roses. And inside the README file will be a URL to a Google Colab. Once you click on that Colab, you'll be brought to this page here, or more specifically, you'll be brought to this full page here. And to run this script, all you have to do is click on one of the cells. So in this case, this code cell, and click, you can click this button here to process, or I used Shift Enter. And then it processes that cell. And it's just connecting and initializing some usage of CPUs. So it's now loading the required packages, and I'll go through what these are in turn in a second. But what I've provided is a collab where the members or the participants of this course are unable to actually comment the code themselves. But if you go into one of the cells, so say this note cell, you write something, say update, like that, and you click enter and change it. And if you then save this, so I normally do the standard hotkey for saving. For me, it saves successfully, but for one of the people with the link that I provided, it will ask you to make a copy of the notebook. And another way that you can do that is by doing file, save a copy to Drive, or to a GitHub, or to a GitHub gist. So what I would suggest doing first is save a copy to your Drive, which will then allow you to update and change this notebook as we go along. But also leave open the original URL that I provided, as on each of these cells, you'll be able to use this button here to add comment. So you can ask questions or for clarity, or you can say if there's something wrong or you think something should be changed. And I'll also get this on my side of things, and everyone will be able to see these comments. Okay, perfect. So I'll just go through the packages that we're using throughout this course, and then we can answer any questions regarding the running of this code first. So the first 2 packages are the most standard in Python, the plotting one, matplotlib, and numpy for the standard processing stuff like square roots. Yeah, these are pretty standard, and I think everyone knows these. We use it tools for one section in the script. This is to create a pairwise problem, and I'll discuss this more when we get down to that section. We use a probabilistic toolkit called PyMC, specifically the 3rd iteration of this package. And this is then added as PM. We also use RViz, which is a visualization toolkit that builds on top of PyMC3. We use another visualization toolkit called Seaborn, which will allow us to do these density maps very quickly. And finally, because we need to use a mathematical function, I've also imported the square root as a simple internal math package. So again, to process this script, process this cell, if we click on it and we do Shift Enter or click that button there, it will then process that specific cell. So I'll stop there briefly to ask if there's any questions regarding the running of these scripts. Okie dokie, fantastic. So I'll just add some additional features because I think it's very important to understand a bit more about Colab as a whole, because this is becoming far more prevalent in the machine learning community in computational sciences. You can actually use these free of charge for a certain amount of time, runtime. There's additional features. So if you click runtime up here and change runtime type, you can actually include or use a free GPU for a given small amount of time. So this allows for more complex problems where you need something like a graphical processing unit or a GPU, you're able to then use that. And this is very useful in addition to actually creating shareable codes, which others can pick up quickly and actually get a handle on what's going on, and even add in these kind of like comment lines as I've done throughout this notebook. So I see Colabs being far more widely used going forward, as you don't need to have this whole infrastructure. All you need is a URL. Okay, so the first section that we'll go through is the setup of a multi-station grid-based earthquake location technique. So I want to start off, and I know there's quite a bit of text here. I want to start off by giving a background to the basic theory of ray-based earthquake locations. So if we consider a seismic array composed of many individual station locations, then the predicted time at each of the station locations, TP being the predicted, I being the station, can be written as TIP is this T term here, and this T0 term, where this T term here is the travel time from some given earthquake source location, or XS, YS, ZS, to some station location, XI, YI, ZI. And these can be shown by these vectors, again, there and there. So then the predicted travel time is then related as the origin time of the earthquake plus the time it takes to get to each of the separate seismic stations. And this T term here is dependent on the velocity structure of the subsurface. So throughout this notebook, we'll do a very simple homogeneous velocity model. But this still holds for more complex problems, except that this velocity structure is changing, and we need to formulate another way to determine the travel time between the source location and each of the stations. And I'll discuss this further in the discussions and conclusions later. So then, to actually determine the earthquake location, we want to take some observational data. So this will be observational arrival times of the earthquake at each of those stations, T0, and use the entirety of the seismic array. And then we can do some minimization between the observed arrival time at each of the stations and the predicted, so this term here. So in this case here, we're representing this misfit as an L1 norm. So just the summation over the difference between the observed and the predicted, where N represents the total number of stations, T0I is the observed arrival time at station I, TPI is the predicted arrival time at station I, given from the above equation. And then this misfit function is represented by R, is then dependent on 4 parameters. So the source location in X, Y, Z, these 3 here, and also the origin time of the earthquake. So we want to learn for a given observational data set what this X, Y, Z, and T0 are. So these are the parameters which we wish to solve for. And in addition to that, this t term is a nonlinear function, and it's not possible to solve this t predicted as an analytical function. So this forms a really complex problem, and several ways that we can go about actually inverting for this difference. So let's start by creating a two-dimensional cross-section. So let's give it a homogeneous velocity model VH. And we position a series of seismic stations on the Earth's surface, we'll call them XC, and compute the predicted arrival times from those stations to a grid of receiver points in the subsurface, using the fact that the travel time from each of the grid cells to the station locations is related by this function here, where xi is a station location, xs is one of these grid cell positions, vh is this homogeneous velocity model. So this is then our predicted travel time from each of the stations to each of the grid cells. So this then creates this travel time that we were showing earlier, and is dependent on this velocity structure VH. Okay, so let's now go through some coded stages here. So we first want to set up a domain of interest. In this case, we have x min, x max, z min, z max. So this is basically saying our cross section across the surface in the x direction, and z being increasing in depth. So we define a region between 0 and 30 with a depth between -2, so 2 kilometers above the surface, and a depth of 10 kilometers beneath. We'll set up a series of synthetic seismic stations. So in this case, we're defining 25. And to make it a bit more fun, we're also going to define, of those 25, 2 that have erroneous results. So this is saying that we're creating a synthetic example where there is some error in the observations. And what I mean by this is we'll have, in a real world case, we'd have a series of seismic stations on the Earth's surface. We'll take the arrival time of an earthquake, in this case, the first wave, so the P wave. And all of those have some sort of uncertainty, and the uncertainty is, for each of the observations, is set as a constant value of 0.15 seconds. And in addition, 2 of the stations also have a random error applied to them as well. So they're very far off the observations. Okay, so what we then do is we're defining the stations here, and initially giving them no location, then they're defining a random location in the x direction and setting their depth to be on the surface. So running that. Okay, perfect. So that's now given us the station locations. We next want to create a synthetic earthquake location. So we just define a random location within the full extent of the x direction. So that's x min to x max, and a depth between the surface down to some depth, which is the maximum extent of the volume. And we're defining a random selection of this location. So this is a random uniform prior. So we've given it some random station locations, all on the Earth's surface, and a random earthquake location. So what this means that all of your notebooks that you're running going forward will have slightly different solutions. But yeah, this is kind of setting up a random case you can run multiple times and see the extent to the problem. Okay, so now we've got a synthetic earthquake location and a synthetic station distribution. Let's now determine some observations or observational times that you would expect to see from that synthetic setup. So we define a constant velocity, or this homogeneous velocity, at 3.1 kilometers per second. And we then determine the observed arrival time at each of the seismic stations from this synthetic earthquake location. So these are the observed time arrival times. For the case of this problem, we just set the origin time equal to 0, just to get a flavor of how this is progressing. And Yeah, so basically the origin of the earthquake is dead on 0, and we're only now including in this original formulation this travel time term here. Okay, perfect. So that creates our observational data. So we then have these as a series of observed arrival times at each of the seismic stations. And again, I said earlier that 2 of the stations were erroneous, or we wanted them to be massively off. So we then take 2 of the random stations and then allow there to be some uncertainty in the observed arrival time. So we define this between negative 0.5 of a second and positive 0.5 of a second. And that then forms these 2 erroneous results. And then in addition to that, as I said earlier, there's some observational uncertainty to all of this data of this 0.15 seconds. So we then also define the observed uncertainty. Okay, perfect. So looking at this another way, if we then plot the station distribution, this here, these pink triangles represent the station locations. This red star represents the earthquake location of our synthetic problem. Okay, so now we've set everything up. We've got some observed travel times from this earthquake to a series of these stations. We've got 2 of these stations which have erroneous results, and each of the stations also have some uncertainty, which we won't include in this first section, but comes in more important in the later sections in this notebook. So now we want to do a very simple case where we're just determining some misfit and trying to recover this optimal hypercentral location. So what we do is define a grid of receiver points, so a grid of points representing this full domain. And we're using an NumPy mesh grid between the Xmin and Xmax with some separation, and Zmin and Zmax with the separation, and then turning this into a series of points by flattening. What we then do is we then want to determine the predicted travel time to all of the station locations as if each of these grid cell points is a possible earthquake location. So these form the predicted travel times from each of the grid points to each of the stations. So then TP is iterated over, and we then use the array that we have, this XC. We take one of the grid cell points, and we then determine the predicted travel time for this homogeneous velocity model. Again, as the source time is equal to 0, we're neglecting that in this simple problem. So that will then go through and create this array of TP, which will be an array of the total number of grid cell points versus the total number of stations. Just running that quickly. There we go. So now we're going to look at some misfit between these to then get an understanding of how the observed arrival times compares with these predicted arrival time at each of these grid cell points. So this case here, we're using a L2. Yeah, so this is our misfit function here. And then we're summing over the 0th dimension. So this is basically summing over the station locations, but each grid cell has a different value. So I'll process that. And then finally, let's now plot our misfit function in space. So this is taking this misfit term. We put it into a log scale to make things easier to see. And then we correct because the mesh grid is off grid cell. And supply a color bar, give the location of the minimum misfit. So this is the argmin of the misfit. And then show our station locations, our original imposed earthquake location, and then set the domains. So if we run this now, what we have here is the red star represents the imposed earthquake location. This kind of green or yellow represents the predicted location. And then the color map in the background represents this L2 misfit space. However, this exercise here has some assumptions put into it. So first, we're not actually including this uncertainty in the observations. Second, we're using this homogeneous velocity model, but I'll discuss that later, and that isn't so much of an issue as the actual what's going into this inversion. So we're not using the uncertainty in the observations. We're not giving a full probabilistic understanding of this earthquake location. What are the other ones? The fact we're only using a single phase in this. So currently we're only using a predicted with a single velocity model, but in many cases you'll have stations of both P and S wave arrival. And also the fact that we're showing this misfit space in only the X and Y, and we're assuming that the origin time of the event is known at T0 is equal to 0. So we're saying that we are imposing the fact that the origin time for this problem is 0. So what I've included here is some examples. These are bonus exercises. So I'll go over what the exercises are and what you should do, but I'll upload the answers to this Colab in a couple of days' time. So you have time to go over the problem yourself and kind of get an understanding of what's going on. And then when you click on the link next time in a couple of days, and I'll post on the Slack to say that it's been uploaded, you'll be able to see how it compares with your answer. So the first thing is that we defined a grid size. So we're actually supplying travel times from a series of grid points. And then we're trying to determine this difference between the true and recovered earthquake location. So if we were to run this again with a much coarser grid, this predicted location would be further away. And that's because we're not supplying it with enough information of this misfit space. But as we go to a finer and finer resolution, there will be some sort of convergence where you're getting closer and closer to this recovered optimal location. And that will get closer and closer to this true earthquake location. So what I'm suggesting in the first exercise is to kind of investigate how the geometry of these stations, so running this multiple times, and changing the grid spacing actually affects these recovered earthquake locations. Yeah. So the second question is that, as I stated, this is only for a single phase. So we're neglecting other stuff. So we're neglecting multiple observational phases, which is basically we're not including an S wave as well as a P wave arrival. We're not including a complex velocity model, but I'll discuss that in discussions, and that's beyond probably this notebook here. And we're also not including these observational uncertainties in the travel time, in the arrivals and the travel time models, which we'll discuss later in the next section. So it's the second point here is to update the scripts above and see if you can include an additional phase arrival with another velocity of 4.5 kilometers per second. So what this would be is your first one would represent, your S wave arrival, and the second one would represent your P wave arrival. So, and kind of investigate how the misfit space then changes with this additional phase. Do you get less misfit because you're increasing the number of phases? If you have a varying array geometry, would you expect that you get a better depth constraint because you now have two phases at the station vertically above it? And just kind of understand how the misfit space changes with the addition of a second velocity. And finally, we currently neglect an origin time. So what you could typically do is add an additional grid search. So you have a grid also in the origin time. But what I would suggest doing is first supply an origin time for the event, and then do your search for that origin time by first defining the misfit between the predicted and the observed. So determine the region which you would have to do the grid search over. This will then help constrain your search values and allows you to pinpoint more closely into the origin time of the event. Okay, perfect. So that's kind of this first section. As I said, these bonus questions are to be filled out by the members at a later time, and I'll post some answers to these so people can kind of see into the problem and see how I approached it and compare it with their own results. So the next section I want to discuss is currently what we've shown above is very similar to the current, the hypercentral inverse software package. So we're not including any uncertainty in the phase arrivals. We're not determining the full posterior distribution of the uncertainty in the earthquake location. We're just simply solving some sort of misfit function. In hypo-inverse, it's the chi-squared, I think, and then inverting for the optimal hypercentral location, and in theirs they determine this misfit about the optimal hypercentral location. However, this information that we've gained from the phase picking at the surface also includes uncertainty. So we may pick a P-wave arrival here, but there may be significant uncertainty in that P-wave pick. And we want to then propagate this through to the earthquake location. And in addition, there is a secondary uncertainty in the travel time model. So although in this homogeneous case, we have this fairly nice form that we can solve, in many more complex problems, we have to determine these travel times through finite element, finite difference, or even more recent neural networking, differentiable neural networks. So in our next section, we'll go through these probabilistic earthquake location techniques and start to incorporate in these uncertainties. But I'll stop here for a minute to see if there's any questions about this first section. Okay, perfect. So the second section I want to go over is this probabilistic earthquake location. So as I was saying a minute ago, we're supplied with some observational data, and this observational data will have uncertainty to it. And like I said, many of the automated machine learning phase pickers do have considerable uncertainty if they're not finely tailored to your specific region, or there's a complex earthquake that isn't within the training data set. So realistically incorporating these uncertainties into the earthquake locations is of importance. Otherwise, you could return very well-resolved earthquake locations which are completely erroneous, or where the uncertainty has not been incorporated. In addition, many travel time models, so this determining the time between the earthquake location and the station locations, uses some prior knowledge of the subsurface velocity. And that could be acquired by seismic reflection, it could be core samples, it could be other geophysical techniques entirely, but they also include uncertainty. So we need to incorporate some uncertainty into the travel times as well. Okay, so just as I said, there's some uncertainty in the automated or manual phase picking, and the subsurface velocity requires some geophysical prior context, and these should both be included. So I won't go too much into the mathematics behind the inversion theory, but we want to determine a earthquake flotation posterior, which is dependent on some observation, in this case, the observations in D, and there's some theoretical relationship, this term here. Given the probabilistic formulation of an inversion presented in Tarantola, and this is a very good text into the actual probability on the inversion theory, and is also discussed in far more detail in Anthony Lomax's work in 2000, which is what the software package non-in-lock was initially started as. We can set up a problem where we wish to formulate the posterior density function of an earthquake location and origin time in many cases. And in this formulation, it's a relationship between the theoretical travel times, accounting now for the origin time, and the observed arrival times. But we do make an assumption on the uncertainties that go into this. So for the phase picking, we make the assumption that the phase pick uncertainty is Gaussian, which in most cases seems realistic. And basically, you would then define your uncertainty by the variance about this Gaussian, about your phase pick. Perfect. So then we have the posterior is then related in this term here. We have a normalizing factor. We have some density function of the prior. And then we have this likelihood function here, which is related to the earthquake location and the, in this case, origin time. But in some scenarios, the origin time can be removed using clever techniques. We'll go on to discuss this in a second. So the added advantage this has over this simple misfit function is we now have the opportunity to actually change this likelihood function for the problem in question. And in the next section, we'll go through some of the typically used likelihood functions. And I've outlined some of the advantages and disadvantages to each of the likelihood functions. And then later throughout this, we'll discuss the uncertainties and how we incorporate the observational uncertainties and the travel time. And then finally, we'll go through an actual, using this simple problem we've defined above, we'll go through an inversion technique using one of the described likelihood functions and incorporating these uncertainties. Okay, perfect. So first things first, let's discuss some of the likelihood functions that are typically used. And just to reiterate here, the software package non-in-log has extensive literature and has very similar likelihood functions. So they actually discuss this Gaussian and another one below. And they have a very, very good software package for the inversion of earthquake locations using this uncertainty in observationals and travel time. So the first likelihood function that we can think of is a Gaussian likelihood misfit. So this is then incorporated into this likelihood function as an exponential. It's 1 over half of the summation of these observed travel times minus the predicted, with this sigma value here taking as the standard deviation in the uncertainty as a combination of both the observational from the phase picking as well as the uncertainties from the travel time formulations. And I'll outline how we incorporate this in the next section. But first, let's go through some of the likelihood functions. So first, the advantages for this is it's simple to compute. It's typically unimodal, so meaning that it condenses down to one kind of glob with a central point, and the uncertainty is then defined by this distribution. However, it's not that good at dealing with outlier observations. And what I mean by that is we have some observation that we're very sure of. We define a low uncertainty. We're then back projecting that with other observations, but this one observation is actually not related to the earthquake or could be mispicked and basically inherently pulls the distribution away from the minimal point. So these outliers can actually massively change your earthquake location probability distribution or posterior distribution, and can really change the earthquake location and give you slightly erroneous results. So, and the final point is that this requires the determination of the origin time of the inversion. So inside these predicted and the observed is this T0 term representing the origin time. So the main two disadvantages here we can address using an equal differential time likelihood function. And this was extensively outlined in Anthony Lomax's work in 2005 and is the standard one that's used in non-in-log. And what this represents over this Gaussian term is the differencing between observational pairs and also predicted pairs. So what I mean by this is, say we have two station locations at the surface. We've got the earthquake location. We'll determine the predicted to each of these stations, and we have the observations at each of these stations. And instead of inverting just the predicted minus the observation as a single point, we're looking at the differences between these two. So the differences between the observations in these two stations and the predicted. And what this acts to do is, because the event has the same origin time, it acts to remove the origin time from the inversion. So we now only have to invert for the X, Y, Z. And this is a great benefit because this reduces the parameter estimation from that of 4 down to 3. So actually in our problem, it reduces it from 3 being XZ T0 to that of just XZ. Okay, so in this case here, we have some observations, some predictions. We have the uncertainty for each of those observations. So this sigma I and sigma J. And the advantages that it has is it drastically reduces the number of outliers. So basically, because we're looking at a difference instead of an individual inversion, we form difference fronts. So when they stack, what we actually see is a more multimodal distribution. So we have one location in our posterior space, which would represent our optimal, but then that outlier would actually create a small local minima. So when we're going through our optimization to determine the posterior, we still get the best solution, but now the outlier has been reduced from the effect of this inversion. So this also has the added benefit that it reduces the parameter search to remove this origin term. And as I said, this multimodal distribution actually is a disadvantage in many problems. And this is because it creates this highly multimodal posterior space. Because if you have more and more outliers, you'll have your global minima and several little local minimas. Okay, and the other thing is because we're now doing differences between all the observations, if we've got 20 stations, as in the Gaussian, we were just inverting the 20 stations. Now we're inverting every pairwise difference. So it will be station A with station A with station B all the way up to the end of your total number of stations. And finally, because these differences are inside this exponential and you're then summing over many exponentials, you're actually summing something called a hyperbolic front. And when these start to condense to a global minima, you actually start to get a good solution. But where it kind of moves further away or there's greater misfit, in many numerical solutions, you start to get these infinite terms. So it actually becomes slightly unstable by the fact that you're stacking inside these exponentials. Okay, and the final.
Sorry to interrupt. Maybe before we go to the last Euclid function, we do have a question about you can describe what you mean by the posterior solution.
Okay, it's a rep. I'm trying to think of a nice way to explain it. It's a representation of the earthquake location, including all the uncertainty in the inversion. So in this case here, what you would get is a posterior space. Would look similar to this here, but where the say the maximum in this posterior space on the map value would represent the optimal earthquake location, but then the distribution would give some uncertainty, some understanding of the uncertainty in the location. So this is very good because this gives us a probabilistic sense, and it's now incorporating these uncertainties in the observations in a statistical way instead of this simple misfit function here. So in this case here, we want to set it up as a posterior space so we can include these uncertainties. Hopefully that explained it. It's a bit. Okay, perfect. So the last likelihood function I want to discuss is a Laplacian differential time. This is something that we include in one of our papers from just going through editing now, where it's very similar to the equal differential time, but now it's a stack over these linear bands instead of these exponential fronts. So we're now looking at the differences in the observations and the predicted like the equal differential time. But this is now a combination or a stack over many of these bands, let's call it. So again, like the equal differential time, this removes the effects of outlier observations. It removes the need of this T0 term. but it also removes this numerical problem when you're actually solving the inversion, where you don't return these infinite values anymore. And yeah, but there still remains the disadvantage here that there's a highly multimodal posterior space, meaning that although we've got a global minima representing the earthquake location with the uncertainty, you may have these local minimas, which makes sampling that space more complex because you may condense to a local minima when actually you haven't met the global. And also we've still got this pairwise, the observations. So we've, instead of just inverting for 25 seismic stations, we've got 25 related to every other station. Okay, so in this problem set, we'll be using this Laplacian differential time likelihood function. And so I've described these likelihood functions, but these terms here represent the uncertainty in the that's supposed to be prior. Oh, okay. The uncertainty, actually no, it's supposed to be posterior. Sorry. Is a combination of the observational, as I said, so these phase rivals, and this forward model uncertainty in the travel time. So using the combination of variances, we can take the variance of the observational uncertainty and variance of the predicted, and say that the total variance uncertainty is then the combination of these two. So for the observational uncertainty, what we'll do for that one is it could be related to your picker itself. So if you're manually picking an earthquake, you would pick the optimal P wave, say, and you would say that I'm not too sure where that P wave arrives. There's some uncertainty to that. So we could say that the standard deviation of that uncertainty is this. So you would then supply that going forward. In more complex cases like machine learning methods, the uncertainty is related to your training window in some respect. So taking something like some of the early GPDs or phase net, yeah, you would define that by your square function or the triangle shape. But going forward, you could use more complex machine learning methods to actually include uncertainty and actually determine the distribution around your phase pick, which could then propagate forward into these problems. Okay, so that defines this sigma observation. So we determine the standard deviation of our phase and phase arrival uncertainty, and then this goes into this term here. The second one that we can incorporate is an uncertainty in this forward model. So as I said earlier, travel times are constructed as the time it takes to get from the earthquake source to a station location. And because the uncertainty would inherently lie within the velocity model that you supplied, as you have uncertainty throughout the source to the receiver point, it would be a combination across the entirety of the path. And that's the most basic form of uncertainty in the travel time formulation. But we can use a similar approach to what Lomax showed in 2000. In the setting in nonlinear lock, it's called LOCGAL2. But instead of using a epicentral distance function, we use a travel time related term to this. So what do I mean by that? Well, our predicted uncertainty in the forward model would be bound between some min and max value. So these are kind of like bracketed. And between those two brackets, we would have a uncertainty that's increasing as a fraction of the predicted travel time. So what this means is that as we get to further and further away station locations from an observation, we're saying, well, the travel time is not really that well known due to the uncertainties in our travel time simulations. So we're now incorporating that into this problem. So the LOCGAL2 setting in nonlinear lock is very similar to this, but instead of t predicted, it's actually a distance function. So it's related to, I think, the epicentral distance away from the earthquake, between the earthquake and the station location. Okay, so this then creates our predicted standard deviation uncertainty. And as I said, there's one term that's the fraction of the predicted travel time, and we also have the minimum and maximum values. So in this case here, we define a sigma min of 0.001. sorry about that, of 0.1 seconds, sigma max of 2 seconds, and a gradient of 0.1. So what this is saying is we are saying there's at least an uncertainty of 0.1 second in our travel time formulations at any distance, but we expect it to increase with further travel times. And this is very useful term in software packages like non-in-lock, because it allows you to actually carefully tailor how you're weighting your station locations into your inversion. So when you make this, this gradient lower and you set a no upper bound, you're weighting the distant stations more than you would if you increase the gradient of this line. And in many cases where you don't have really well-known velocity models, so for example, if you're next to a volcano, you may have a prediction of the local 1D velocity structure, but as you move away or as your stations get further and further, they could be distorted by near surface velocity contrast, which you haven't accounted for. So this really helps in the inversion for earthquake locations where you don't have a very good velocity model. And as you get better and better velocity structure through other geophysical techniques, you can actually reduce the effects of this predicted term. Okay, perfect. I can see that I'm running slightly slow on time, so I'll go through the next section slightly quicker. So I'll go through this section first, and then if there's any questions, we can discuss it at that point. I think that's probably the best way to do it. So this is the main code for the problem. So as I said, we're doing stuff pairwise for our likelihood term. So what I'm saying is if we got 25 stations, I want to take the first station with the second station, the third, the fourth, the fifth, all the way to n. For the second station, I want to do the same. So we want to determine every pairwise combination. So I use these iter tools combinations to determine the pairwise. This likelihood function here represents this Laplacian differential time likelihood with the predicted, the observations, the sigma being these the observational uncertainties for station IX and station IY, or the index for the station IX. And then this is our likelihood term, and then we sum over them. And finally, this is the bulk of our inversion procedure. And for the context of this problem, I won't go through the sampling method too much. But if you're interested, we're using a Metropolis Hastings Monte Carlo method for sampling of the posterior. And how we're doing this is we're defining an earthquake location that could be somewhere within the bounds, and it's uniform prior, of a lower, basically within the bounds of our domain of interest. We'll then have some predicted travel times for each of the grid points in our problem. We'll have our observed travel times, our uncertainty in our observed data. We'll have the station locations, XST, ZST. We'll then do the predicted travel times from each of those grid cells to station locations. We then define our predicted sigma. So this is this bounding problem. So this is accounting for the travel time model uncertainty. We'll have some sigma zero term, which is the observational one. And then it's the combination of these two to determine the standard deviation here. Then our likelihood function is the one that's supplied to this MCMC. We go through our sampling, we define our sampling method, which is Hamiltonian Monte Carlo. We then sample from the space where we draw a certain number and we tune. So what I mean by that is we do so many draws and the tuning stage is things that are removed in the sampling method. I normally use 10%. And then we draw samples from the recovered posterior. And then we can plot how well our recovered looks as the parameter space. Okay, so hopefully there's enough information here to get a sense later when you come back to look at this of what's going on. What we return is something called the trace, which is giving an information about the sampling method, a summary of the uncertainty in the earthquake location and the optimal location, and then also provide some samples which you can then use for plotting to look more into the posterior space. We then run this. This is one I did earlier. This doesn't take too long to do. It's roughly a minute to run here. So this is the two chains that we used for our sampling, first and second. This is then drawing from this distribution. These are then returning the mean values, standard deviations, and the HDI indexes. And these then represent the trace plot. So this tells us more about the distribution and whether we've actually realistically sampled the posterior. So this shown here is the number of iterations through our MCMC or Hamiltonian MC. So the fact that this is all roughly one level with some uncertainty about it gives us the distribution here, and the same shown here. So this then gives us the uncertainty in our optimal hypercentral location, but this is kind of showing a condensed form of just each of the dimensions. So now let's plot this in respect to the mean predicted location from the Hamiltonian Monte Carlo and the one imposed. So now we got this distribution here where that mean prediction is there. The red star represents our imposed earthquake location, and the blue color map represents the uncertainty in our location, taking into account these model uncertainties and these observational uncertainties. Okay, so hopefully this should be fairly similar to follow. This is the same example as shown in the first section. I'm just now showing the probability. You can now tailor this to your problem. You can change this likelihood term here to be the equal differential time. You can increase the number of draws and see how that changes. And yeah, you can then change the predicted uncertainties and the observational uncertainties and see how it changes this problem. So I've shown this currently for a Laplacian differential time function. What the bonus exercise for is to investigate including an equal differential time. So I've given you the equation. I've shown you how the Laplacian differential time function is written. So now the exercise would be to write a Laplacian, write the equal differential time likelihood function, and then rerun this to see how it changes the posterior space. So that means writing something similar to this here, but now for the equal differential time. And then that would change the likelihood function going into the problem. Okay, so that's one to do later. And then the final question would be, earlier I said there was some bogus observations going into the problem. So I said that two stations had false data. Then the other problem is to try and look into the data and actually plot the observational times versus the predicted for the optimal hypercentral location and for the samples drawn from the posterior to get a sense of how the uncertainty in the earthquake location plays a role into the uncertainty in the predicted arrival times and how it compares with the observations. And this should allow you to kind of get into the fact that those observations were those observed arrival times at the stations were poorly defined with the uncertainty. So can you then include these uncertainties to then bring them back in line within the uncertainty in the earthquake location? Okay, so I'll stop at that point here and ask if there's any questions.
Yeah, we actually have a question.
Okay.
So about the fact that the MCMC, and the question is, the MCMC inversion result isn't that good because we've taken the mean of the sampling space to be the solution. So the question is, doesn't it make more sense to take the maximum or the median?
Yeah, so for the case of this, I just put down the mean, but yeah, you're right. You should take the maximum in this case. Yeah. But in a case where you would have multi-mode distributions, it could be that maximum would be distorted by other local minimums. So I normally hedge a bit on mean values, or you would have to go into some categorization of this like local distribution, and then you could take the maximum. So that was my initial idea, but it wasn't as complex as I was expecting. So maybe maximum was a better idea. Perfect. Okie dokie. So the last section I just want to discuss, this is a very simple problem that we've defined here, but the crutch or the methods outlined here are applicable to more complex geophysical problems in real world cases. And there's only a couple of tweaks that would be required to turn this into a real world use case or code. So I'm just going to go through this 3 points here. So the first one is the inclusion of a more complex travel time model. So in something like non-in-loc, you would compute travel time simulations or formulations by understanding, you would supply it with a velocity structure, typically a one-dimensional one increasing in depth, where you've included how the lithology is changing. And you would then compute a finite difference forward model that's solving the iconal equation. And the iconal equation is what's relating the travel time with the velocity structure. And normally these formulations are done for in each station case to a grid of receiver points. So you would give it the station location, you would give it the velocity structure, let's say P wave, and a grid of your subsurface, and you would then run the simulation to determine travel time from the station to the points. And for more complex problems like 3-dimensional, the same thing holds, but now with the 3-dimension velocity structure. However, in more recent work, there's been some work done on this kind of approach to structure the problem not as a grid. And this is work that we actually did back in 2020, where we're using machine learning based methods to solve this iconal equation using a neural network and some inherent features that make neural networks very good at solving partial differential equations. And in this formulation, we supply a velocity structure, and we can then determine the travel time between 2 points after the model has been trained. So this then just changes this first equation that I showed, this T term, where you would then just supply this neural network with a station location or a series of station locations and a source location, and you'd immediately pop out the travel time between the two. Yeah, so as I said, this can then just act to replace this predicted travel time. And there's many methods that you can go about using, several methods to determine these travel times. Yeah, but this one is the standard one that would be used in something like software package like non-in-loc. And this one here, the neural network one, is used in our software package, which I'll define down here. Okay, so that's changing this travel time term. So now we've got a more complex problem. There'll be inherent features that come out of that. But again, we've only got this as a earthquake location in 2 dimensions. So we would add in this additional term, so X, Y, Z. And in the real world, it gets more complex than that because you also have to allow for difference in reference frames. So you could use something like PyProj. Yeah, I can add that in, which will then predict between different reference frames. But typically you would do this inversion in something like a kilometer reference frame so that all the dimensions have the same values. And then you can go between something like a local reference frame to a global latitude and longitude. So again, that could just be included. So you take your initial station locations, project them to your local coordinate system, do this whole procedure, get your earthquake location and project back to your global reference frame. And finally, this notebook has actually outlined an earthquake location using a small number of seismic stations. And in some cases, you will have small deployments, small seismic stations, local deployments. But for larger data sets, like you're starting to see on these high density seismic deployments, so there's one in Los Angeles called Long Beach, which is a high nodal array. And also in many DAS cable systems, they actually discretized the continuous data to a series of discrete points. But there's a large number of synthetic stations then. So normally each cable would be around 2,000 stations. Inverting those using this simple problem above, using Hamiltonian Monte Carlo, becomes a bit of a computational nightmare. And actually, looking through this whole posterior space and determining this global minima with the uncertainty can take hours in some cases. As such, additional methods are needed to efficiently sample this posterior space. So non-in-loc, this software package, as I stated many times, actually uses a method called octree. So this is subcategorizes the domain into a series of grid cells, and that then helps it converge much quicker than something like a grid search, and in some cases better than Hamiltonian Monte Carlo. And in our work currently on archive, currently in press, we actually use a more recent Stein variational gradient descent. I won't discuss that in more terms, which actively samples a series of points and updates the position of all the points together to better represent the posterior space. And we actually show for complex problems, we've got 2,000 plus observations. It takes not that much time to actually process to get an earthquake location. And then this is also leveraging travel time formulations using machine learning methods. So this is a fully developed machine learning package that's basically getting earthquake locations from observational data and your velocity structure. Okay, so the final remark in that is, although this problem in this the problem outlined in this notebook works very well for this small deployment number, you need to actually update the sampling method or the representation of this posterior when you get larger number of stations. And in a world where seismic instruments are getting cheaper and cheaper to deploy, we carry them around as some people are starting to use phones. It's very important to be able to incorporate as much data as possible into the inversion scheme. So at that point there, I've dropped some references below. I'll take any questions as concluding remarks.
Thanks a lot for that. Yeah, to our participants, feel free to post any questions in the chat or the Q&A box for a while.
I'll be around after the call if there's any questions that anyone wants to ask.
Great. Well, yeah, I would say if there are no questions, well, yeah, feel free to post them on Slack, as Dr. Smith said. Yeah, thank you all for attending today's session. Please feel free to tackle the exercises in the notebook. And yeah, we'll upload today's lecture to YouTube within the next 24 hours, and we'll have a Google form posted for you all to log your participation. And we'll be back next week for a lecture on seismoacoustics. So once again, thanks a lot, Dr. Smith. That was a really cool overview of a really classical inverse problem. It's really fun.
Yeah, there was quite a lot of information in there. Sorry if it dragged on a bit, but I think it's quite good to get an understanding of the fundamentals. If you want suggestions for software packages or methods, don't hesitate to ask in the Slack.
Great. Thanks a ton. Well, I think we'll probably end the recording there. See you all.